Brain teaser. 2 clear liquids go into a polarimeter. The readout for sample A is plus 10 degrees, while sample B reads 0 degrees. Which sample is racemic? Is it A, B, neither, or both? You've got 5 seconds. Go. Time's up. The answer is sample B. A racemic mixture contains equal amounts of both enantiomers, so their opposite rotations cancel to 0. In this video, you'll learn what enantiomers are, what plane-polarized light is, how optical activity works, how to measure specific rotation and enantiomeric excess, and how to avoid common pitfalls. Enantiomers are non-identical mirror image molecules. In an ordinary achiral environment, they share the same melting point, boiling point, density, and polarity. However, they differ in one standout property: the way they rotate plane-polarized light. Ordinary light vibrates in many planes. A polarizer lets through just one plane, creating plane-polarized light. If that beam passes through a chiral sample, the plane rotates by some angle alpha that we can detect with an analyzer on the other side. One enantiomer rotates light clockwise, dextrorotatory, labeled plus. Its mirror image rotates the same magnitude counterclockwise, levorotatory, labeled minus. Important note to remember, plus or minus does not tell you R or S configuration. So far, we've defined enantiomers, built a picture of plane-polarized light, and named the 2 rotation directions, plus for clockwise and minus for counterclockwise. Ready to lock it in? Tap the link for study guides and flashcards on this topic, so you can keep learning without missing a beat. How do we quantify this? With a polarimeter. The observed rotation, alpha, depends on the sample path length, or L, and concentration, or C, as well as temperature and wavelength. Most commonly measured at 20 degrees Celsius, using the sodium D line at 589 nanometers. Chemists report the normalized quantity-specific rotation, written alpha T lambda equals observed alpha over L times C, with L in decimeters and C in grams per milliliter. Let's use a simple worked example. Suppose a pure plus enantiomer rotates plus 10 degrees under given conditions. Your unknown sample, measured the same way, rotates plus 2 degrees. The enantiomeric excess is 2/10 times 100 equals 20%, and the major enantiomer is the plus 1. A perfect 50-50 racemic mixture gives alpha equals 0 degrees. But 0 rotation can also mean the molecule is a chiral, like a meso compound with an internal mirror plane. Context and structures still matter. Why does any of this matter? Because in chiral settings, like biological receptors, enantiomers can interact differently. That's why one enantiomer of a compound can smell like spearmint, while its mirror image smells like caraway. However, beware of common pitfalls. Mixing up plus with R or S, overlooking temperature or wavelength when comparing rotations, or forgetting the units when calculating alpha. Instead, follow this guided step through. Check chirality. Measure alpha under defined conditions. Compute alpha using L and C. Compare it to the pure enantiomer. Then infer enantiomeric excess and sign. If alpha is close to 0 degrees, test whether the sample is racemic or intrinsically a chiral. To recap, enantiomers are mirror images that rotate plane-polarized light in equal and opposite ways. Polarimetry turns that rotation into numbers, specific rotation, and enantiomeric excess, to judge purity. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.